This is a classic and very interesting proof-based problem. We have a cube, and suppose that positive integers are written on all faces of the cube, such that they sum to 11. Now, you want to prove that there exists two faces sharing an edge with the same number written on them. Now, at first glance, this problem does not look very easy because there are a lot of ways in which you can have the numbers sum to 11. So doing casework or even some sort of global approach with casework is not going to be effective. So what's our approach? Well, we can maybe consider a vertex. And the reason that a vertex could be pretty useful is because notice that for each vertex that you choose on the cube, there are exactly 3 square faces that share this vertex. So for this vertex, there's this face, there's this face, there's also this face. These 3 faces share this vertex as, well, a vertex. So that's cool. But what's even more helpful is that notice that within these 3 faces, if you choose any 2 of them, they share an edge. So if you could perhaps prove that within these 3 faces, there are at most 2 distinct values, you would prove this instantly. Okay, that's definitely something to keep in the back of our heads. But what detail should we focus on about those 3 faces? Maybe the sum of the numbers on them? Sure, why not? Let's give it a try. We should always try something if it clicks with our intuition. Or even if it does not immediately click, still try it. You can get some progress from it, potentially. So we need some proper notation. I'm going to name this vertex V1. And I'm going to name all the other vertices. So this is V2, V3, V4, V5, V6, V7, and V8. Now, I'm going to define f of Vi for I equals to 1, 2, all the way to 8 to be the sum of the 3 numbers written on the 3 faces which share Vi as a vertex. So for instance, f of V1, well, that's going to be the sum of the 3 numbers on the 3 faces which share this vertex, which share V1 as a vertex. Now, I want you to consider the value of f of V1 plus f of V2 plus all the way to f of V8. What is this sum? Well, this is actually not very hard to calculate. Notice that, okay, take the face defined by this vertex, this vertex, this vertex, and this vertex, okay? Notice that within this sum, when you add f of V1, you count the number on this face 1 time. And when you add f of V2, you count the number on this face another time. And when you add f of V3 and f of V4, you count that number 2 more times. So within this sum, you are actually counting the number on this face 4 times. And by symmetry, the number on all faces of the cube will be counted 4 times within the sum. So in fact, this sum is just equal to 4 times the sum of the numbers on the faces of the cube, which is 11. So this is 4 times 11, or 44. So why is this so useful? Well, check this out. Consider the smallest of these 8 numbers. Right? There are 8 numbers being added in this sum. I want you to consider the smallest of them. Without loss of generality, assume that f of V1 is the smallest of them. Now, if it's the smallest, then we know that this quantity must be smaller or equal to 44 divided by 8. Right? Because the sum, we have a sum with 8 numbers adding to 44, so the smallest of those terms must be smaller or equal to the sum divided by the number of terms. And if you were to evaluate this, this is equal to 5 point something. We don't need to know the exact decimals. So what is this inequality telling us? Well, it's telling us that the 3 numbers written on the 3 faces that share vertex V1, their sum is smaller or equal to 5 point something. But think about it. If the 3 numbers on these 3 faces were all distinct, then the minimum sum is 1 plus 2 plus 3, which is 6. But that would be a contradiction because 6 is definitely not smaller or equal to 5 point something. So therefore, we've deduced that among these three faces which share v1, there can be at most two distinct values. Not three, at most two distinct values. Well, that would instantly prove this statement. So therefore, this contradiction proves the desired result. Throughout this problem, I hope you took away that it's usually a good idea to think of quantities that do not change. So for instance, this unchanging sum of 11 helped us evaluate a very helpful expression. Now, of course, it's not like in all problems you'll be given the invariant quantity, but when you do find such a quantity, that could be super useful, especially for proof-based problems. We also used something called the extremal principle, which is a technique where you focus on the smallest or the largest of some quantity within the problem setting. So for instance, we focused on the smallest of these values, the smallest of the 8 values within this sum, which helped us derive a constraining condition and provide a contradiction. If you just focused on some random term within this sum, that would not be convenient. You would not be able to derive this condition. So definitely think of a term with the most restriction, not just some random term. Okay, well, that's going to be it for this video. I hope you learned something. I hope you found it interesting. If you did, then please consider dropping a like and subscribing. Thank you very much. Bye.